Okay, let's dive in. Today, we're cracking open a research paper exploring a fascinating area, zero-shot text-to-image generation.
Really interesting stuff.
We've got the source material right here, and our mission is to extract the absolute core insights, understand the clever methods they employed.
And figure out what it all means, right?
Exactly. Figure out what the results truly signify. Think of this as your direct line to the essential knowledge in this cutting-edge work, without needing to wade through, every technical sentence.
Yeah, a shortcut to the good stuff.
And spoiler alert, the big takeaway isn't some wildly complex new design, but something surprisingly straightforward when you just make it really big.
That's pretty much the essence of it, yeah. Text-to-image generation has been a goal for a while now, but this paper suggests maybe we were overcomplicating things.
By not going big sooner.
Exactly, by not embracing scale sooner.
Okay, let's set the stage then. The paper gives us a little history lesson. What were some of the early attempts at getting computers to, draw from text?
Well, you're looking back to around 2015, give or take. Models trying to condition standard generative architectures, things like DDraw or JANS.
Right, the usual suspects back then.
Yeah, conditioning them directly on image captions. The idea was simple enough. Take a text description and make the model produce an image that matched.
So you'd show it a bird on a branch, and it would, try to conjure that image.
Precisely. But as the paper highlights, these early attempts, and even, some later ones, often required quite complex setups.
Like how complex?
We're talking intricate custom architectures or auxiliary losses added during training, sometimes even needing extra data like object labels or segmentation masks to help guide the model.
Okay. So basically you had to give the model a lot of hints like this pixel belongs to the bird, this one to the branch, a lot of hand-holding.
Exactly. You were kind of trying to engineer solutions for specific parts of the problem, piece by piece.
And even with all that effort, what was a common problem mentioned in the paper regarding the images these models produced? They weren't perfect, right?
Far from it, often. Despite the complexity, the generated samples could still suffer from significant issues, visual artifacts, weird glitches.
Distorted objects.
Yeah, distorted objects or things just being placed illogically within the scene. Getting a coherent, high-quality image that truly matched the caption was, well, a major challenge.
Okay, so complex methods, extra data, and still facing hurdles with quality and coherence. This leads us directly to the central question this paper poses.
Right.
Maybe the limitation wasn't the architecture's complexity, but simply the scale, the size of the models, and the data being used.
That's their core hypothesis. They wondered if scaling up substantially could overcome some of the fundamental issues faced by prior smaller models, even if those models used more, let's say, specialized designs.
Which brings us to their proposed approach, which they describe as simple, which sounds almost counterintuitive after what you just said.
Well, simple in concept, maybe. The idea is to adapt the successful transformer architecture, which has been, revolutionary in language processing.
Sure, everywhere in NLP.
And apply it to a combined sequence of both text and image data. They treat the text description and the visual representation of the image as a single stream of tokens.
Okay.
And train a large transformer to model this sequence autoregressively, predicting each token based on the ones that came before it.
So hang on. Instead of building a custom image generation machine, they're essentially saying, let's just use a massive general-purpose sequence predictor on both text and image data mashed together.
That's the conceptual shift, yeah. But as we said up front, the massive part is absolutely key here.
Right.
This relies on, and they emphasize this, sufficient data and scale.
Yeah.
We're talking about a 12 billion parameter transformer model.
12 billion, okay.
Trained on a huge internet-scale data set of 250 million image text pairs.
Wow. Okay, 12 billion parameters. That's definitely not simple to train, I imagine, but the idea itself compared to those complex earlier architectures.
Right. The architectural concept is simpler, less bespoke engineering for the image part.
And what's their big claim based on this scaled-up, simple approach? What do they say it achieves?
Their claim is that this approach, despite its architectural simplicity compared to some specialized models, achieves competitive results even when evaluated in a zero-shot fashion.
Zero shot. Meaning the model hasn't been specifically fine-tuned on the particular data set or task it's being tested on?
Exactly. You just take the big pre-trained model and test it directly. And they state this results in a flexible, high-fidelity generative model.
Achieving high quality and flexibility zero shot with just a general architecture. That'd be a huge leap, wouldn't it?
It really would. It suggests a different way forward.
Okay, let's get into the nuts and bolts of how they actually implement this. They mentioned it's a two-stage process, and crucially, they don't work directly with raw pixels. Why avoid pixels? Seems like the obvious way to represent an image.
It seems obvious, but handling raw pixels, especially for images large enough for interesting details like, say, 256 by 256 color images, requires an enormous amount of memory and computation, especially for a model of this scale.
Just too much data.
Way too much data per sample. And also, training directly on pixels can sometimes lead models to focus excessively on tiny pixel-level details like local textures rather than the larger structures and objects in an image. The bigger picture.
Right, losing the forest for the trees. So stage one is designed to handle that, to get around the pixel problem.
Exactly. Stage one involves training a discrete variational autoencoder, or DVAE.
Okay, DVAE.
Think of this as a learned compression mechanism. It takes a high-resolution image, like that 256 by 256 color image, and compresses it down into a much smaller grid of image tokens.
Image tokens.
Yeah.
Like creating a simplified vocabulary for visual concepts. Almost like words, but for picture parts.
Yeah, that's a good way to think about it.
Huh.
A learned visual codebook, they compress the image into a 32 by 32 grid of these tokens, which gives you 124 tokens total.
Okay.
And each token can represent one of 192 possible learned visual patterns or concepts. The DVAE learns this mapping, how to turn pixels into tokens, and crucially, how to turn tokens back into pixels for viewing.
And the big win here. Why go through this trouble?
This compression dramatically reduces the sequence length the main transformer has to process. You go from, 256 times 256 times 3 color channels?
Which is nearly 200,000 numbers.
Right, down to just 1,024 tokens. That's a reduction factor of 192. It makes training a massive transformer on images actually feasible.
Wow.
And the paper shows, in figure 1, that the DVAE can reconstruct the original image from these tokens without a large degradation in visual quality. The reconstructions look pretty good.
Okay, so the DVAE turns the image into a short sequence of these visual tokens. What happens in stage 2 with the giant transformer, the main event?
Stage 2 trains the main event, the 12 billion parameter autoregressive transformer. Its job is to model the joint distribution of text and image tokens.
Joint distribution, meaning how likely text and image patterns are to occur together.
Exactly. They concatenate the text tokens, processed using a standard method called BPE byte pair encoding.
Right, that just breaks text into common subword units.
Yeah, handles vocabulary size. So they concatenate those text tokens, up to 256 of them, with the 1,024 image tokens from the DVAE.
So the model sees a sequence that looks like some text tokens followed by a bunch of image tokens.
Correct. That's the input sequence format. And the transformer, which is a decoder-only sparse transformer.
Sparse meaning it doesn't look at everything all the time. More efficient.
Right. It uses attention mechanisms that are more efficient for very long sequences by not having every token attend to every previous token. It focuses attention in specific structured ways, like locally or based on row columns for images.
Okay.
And this transformer is trained to predict each token in this combined sequence based on all the tokens that came before it, whether it's predicting the next word or the next image token.
So modeling that joint distribution,
Yeah.
What does that mean in practice for this model? How does that help generate images from text?
It means the model is learning the statistical relationship between text and images simultaneously from that huge data set. It learns which image token sequences are likely to follow which text token sequences. Ah, okay.
And also, which image tokens are likely to follow other image tokens to make a coherent picture, all while being guided or conditioned by the initial text description.
So the text influences the start of the image generation, and then the model continues based on both the text and the image parts it's already generated.
Precisely. This allows the text description to directly influence the generation of the image tokens that follow.
And how does the attention mechanism work across the text and image parts? Does the image part look back at the text?
Yes, that's crucial.
Yeah.
The image tokens are allowed to attend to all the preceding text tokens. So when it's deciding the next image token, it can consider the entire text prompt.
Makes sense.
For the image-to-image part, predicting subsequent image tokens based on previous ones, they use those different sparse attention masking patterns we mentioned, like focusing only on tokens in the same row or same column or in a small convolutional-like window, mainly to manage the computational complexity of predicting a large grid sequentially. Got it. Okay. So Compress images into tokens, feed those tokens along with text tokens into a gargantuan sparse transformer that learns the combined patterns.
That's the core method.
Now, the big question,
Hmm.
did it actually work? Let's look at the results, starting with the quantitative side,
Yeah.
the numbers.
Right. So they evaluated the model in that zero-shot setting we discussed on standard image caption datasets like MS-Cacao and COB,
And compared it to?
compared it to prior leading models, mostly Jan-based ones like AttenJan, DMJan, and DFJan, which were state-of-the-art or close to it at the time.
Okay. How did it perform on MS Coco? That's the more general data set, right?
Yeah.
Lots of different objects and scenes.
Yeah, MS-Coheos is quite diverse. On Honest Cocoa, the results were actually quite strong, especially considering it was zero shot. They achieved high quality and, importantly, in human evaluations.
Ah, asking real people.
Yes. When people were shown images from their model in a leading prior work, DFJan for the same caption, humans preferred their model samples 90% of the time for overall realism.
90%. That's huge.
And 93.3% of the time for best matching the caption, which is arguably even more important for text to image.
Wow. Okay.
They also report FID scores. FID is a common metric for image quality and realism. Lower is better, and their model achieved a competitive FID score compared to the baselines. Again, zero shot. You can see that in Figure 9A on the paper.
Human preference is that high zero shot.
Yeah.
That's a powerful indicator. But you mentioned another data set, CUB birds, right?
Right. CUB is specialized for fine-grained bird categories. And this is interesting. On CUB, the model fared significantly worse zero-shot. Figure 9B shows this quite clearly.
Worse how? Like the bird quality wasn't good.
Yeah, the FID score was much higher, indicating lower quality or realism compared to models potentially trained or fine-tuned on bird data. The paper speculates that this general approach, trained on broad internet data, might be less effective on such narrow, specialized distributions without some form of fine-tuning. It might not capture those subtle fine-grained differences as well out of the box.
Okay, so it seems scale plus generality works incredibly well on broad data, like MS-Scale, capturing the general gist and look. But maybe it struggles a bit on very specific niche domains without adaptation. That makes some intuitive sense.
It does. Specialization might still require specialized data or fine-tuning.
Do they use any tricks to boost the quality further, like generating multiple images and picking the best one?
Yes, exactly. They used a re-ranking step, which is pretty common in generative tasks. After generating multiple potential images for a given caption, say 64 or 128 images, they used a separate pre-trained contrastive model like CLIP, or similar to score how well each generated image actually matched the text query.
So an independent judge.
Right. And then they just selected the highest scoring image as the final output. The paper shows that generating and re-ranking more samples generally improves results, but there are diminishing returns.
Makes sense.
Figure 6 and Figure 9C show that things get better as you increase the number of samples you re-rank, but the improvement starts to level off after around n equals 32 or so.
Re-ranking makes sense. Generate a bunch, pick the best one. Okay, the quantitative results are solid, especially on the general data set. But honestly, for me, the truly mind-blowing stuff isn't just in the metrics.
Yeah.
It's in what the model learned to do just by being massive and trained on this simple objective.
Let's talk about those qualitative findings, the emergent capabilities. This is where it gets really interesting, right?
Absolutely. This is where the magic, so to speak, happens, and you really see the power of scale manifest in unexpected ways.
Yeah.
The model developed abilities it wasn't explicitly trained or designed to do.
Like what? Give me an example.
Well, for instance, it could combine distinct concepts in novel and often surprisingly plausible ways. Their famous example, the one everyone remembers, is generating images for the caption, "A taper made of accordion."
A taper made of an accordion.
Yeah. And the model produced images, shown in Figure 2A, where the taper's body or skin actually has the texture and structure of an accordion bellows. Wow. Okay, that requires more than just drawing a taper and drawing an accordion. It requires some kind of conceptual blending, understanding both things and how to visually merge them.
Exactly. It suggests a deeper level of compositional understanding emerging from the data. Another emergent ability was handling combinatorial generalization and even rendering text.
Combinatorial generalization, meaning putting things together correctly.
Right. They show the example, an illustration of a baby hedgehog in a Christmas sweater walking a dog. Figure 2B, 2C. The model needs to correctly bind the Christmas sweater attribute to the baby hedgehog, not the dog.
Right. You shouldn't put the sweater on the dog.
Exactly. And it needs to generate both creatures in a plausible scene. Though they do note this variable binding, as they call it, is sometimes inconsistent. It doesn't always get it right.
Still, pretty impressive at work sometimes. And rendering text.
Yeah, it could also render specific text within an image, like creating a neon sign that actually says backprop, also in Figure 2C. That's quite something for a model just predicting image tokens.
That is pretty sophisticated for a model just predicting the next token in a sequence.
Hmm.
Did it learn any other visual manipulation tricks, things you'd normally need, like Photoshop for?
Yes, and this was particularly surprising because it often requires dedicated models or methods. Rudimentary zero-shot image-to-image translation controlled purely by language.
Image to image, like changing an existing image based on text.
Kind of. They could feed the model the image tokens representing, say, the top half of an image, maybe photo of a cat,
Okay.
and then provide a caption like the exact same cat on the top as a sketch on the bottom. And the model could then generate the bottom half of the image as a sketch of the same cat, following the textual instruction. You see examples in Figure 2 and Figure 14.
Whoa. So it could take part of an image and transform the rest based on text? Could it change the style, change the color, like same cat colored red?
Precisely. Or apply a style like postage stamp.
Right.
Or generate a close-up view based on the text, all just from a text instruction combined with part of the image information fed in as tokens.
That's wild.
And the paper emphasizes they made no specific changes to the training objective or architecture to encourage this kind of image manipulation capability. It just emerged.
It just happened from the scale in the data.
Apparently so.
Yep.
It emerged from learning that joint distribution of text and image tokens at a massive scale.
That is genuinely surprising. It suggests these models are learning much more about composition, style, and maybe even object identity than we might initially assume just implicitly.
Yeah, deeper structures in the data.
But okay, making a 12 billion parameter model work that isn't trivial. You don't just press train, right? What were some of the technical hurdles they faced in actually training this beast?
Oh, for sure. Training at this scale on, they mention, 124 GPUs. That's a monumental engineering feat in itself.
1,000 GPUs. Wow.
They discuss challenges with mixed precision training. That's where you use lower precision numbers like 16-bit floats instead of the standard 32-bit.
To save memory and speed things up.
Exactly. But they found that past a certain model size, around 1 billion parameters or so, they started facing numerical instability. Specifically, gradient underflow.
Gradient underflow. The gradients, the update signals, they get too small.
Too small to be represented accurately in 16-bit precision. They basically become zero.
Ah, so the model stops learning effectively. The numbers just disappear.
Effectively, yeah. Parts of the network stop updating. Their solution, which they frame as a practical alternative to more complex methods like custom optimizers, was per-Rees block gradient scaling.
Per Rees block, meaning for different blocks of the network.
Right. They show it in Figure 4. Essentially, scaling the gradients for different residual blocks within the transformer independently to keep them within a numerically stable range for 16-bit representation.
Okay, a clever practical trick. And what about the distributed side? Coordinating all those GPUs must have been a nightmare.
That introduced its own set of bottlenecks, absolutely. First, just getting the entire 12 billion parameter model to even fit into the GPU memory required distributing the model parameters themselves across different machines.
Spreading the model out.
Yeah, a technique called parameter sharding. Figure 5 illustrates their setup. You split the model's weight matrices across the GPUs.
Okay, so the model fits, then what's the problem?
Once the model fit, the primary bottleneck shifted to communication. Specifically, the communication needed to average the gradients calculated on each GPU across all 124 machines after each step.
All that data flying back and forth.
Exactly. It slows things down massively. So they used gradient compression, specifically a method called Power SGD. Table 1 shows it achieved around an 85% compression rate on the gradients.
85%, that's huge.
Yeah, significantly reducing the amount of data needing transfer between the GPUs, which speeds up the whole training process considerably.
So they had to solve major practical problems with numerical stability and inter-machine communication just to make this giant model feasible to train in a reasonable time frame.
Absolutely. Cutting-edge modeling often requires cutting-edge engineering.
Pulling all this together then, what's the central message, the main conclusion this paper delivers?
I think the paper's key conclusion is that a surprisingly simple, autoregressive transformer architecture.
Simple in concept.
Simple in concept, yes. When trained on sufficient data and pushed to an unprecedented scale, both in model size, 12 billion parameters, and dataset size, 250 million pairs leads to significantly improved generalization.
Performing well on unseen data.
Right. And critically, those surprising emergent capabilities we talked about, even in a zero-shot context without specific task training.
So the simple architecture isn't the trick on its own. The scale combined with the simple architecture is the trick.
Precisely. It suggests that maybe simply scaling up these general-purpose sequence models and feeding them vast amounts of multimodal data might be a powerful, perhaps previously underestimated path towards developing models that can understand and combine concepts in really flexible ways.
And perform tasks they weren't explicitly optimized for, like that image manipulation stuff.
Exactly. Tasks that seem to require deeper understanding just
Yeah,
emerge.
that's a powerful idea. We've gone from models that struggle to draw a basic bird through all these complex specific architectures trying to fix specific problems,
Hmm.
to now seeing a massive general model that can compose totally novel concepts like tape or accordion and even manipulate images based on language, all without specific training for those tasks. It's kind of mind-bending.
It definitely changes the landscape of what we think these models are capable of learning implicitly just from raw data correlations at scale.
Absolutely. And that leads me to a final thought for you, the listener, to carry with you. Considering how just modeling text and image tokens together at this massive scale
Yeah.
unlock these unexpected abilities,
Yeah.
like combining disparate concepts or performing rudimentary image transformations controlled purely by language. What other complex visual or maybe even cognitive tasks might simply emerge in even larger, more general models trained on even vaster data sets in the future?
Right. What else is hiding in there?
Exactly. What else might these models be implicitly learning from the sheer volume of data they process that we haven't even thought to test for yet? What capabilities are waiting to pop out at the next order of magnitude?
That's the exciting and maybe slightly daunting question, isn't it? Where does this scaling path lead?
It certainly is. Thanks for joining us for this deep dive into the surprising power of scale in text-to-image generation.
My pleasure. Fascinating paper.
We'll catch you on the next one.